Welcome, everyone. Today, we're going to completely demystify how software actually works. I mean, we interact with apps every single day, right? But how do we truly communicate with these machines? In this explainer, we're diving into the absolute foundation of programming. We'll be looking at the legendary C language, taking raw code, and watching it transform right into reality. Let's get into it.
Okay, let's ground our thinking with a question that might seem a little out of place. How do you tell a machine to make a strawberry milkshake? Seriously, think about it. We know computers aren't inherently intelligent. They don't assume things, and they absolutely do not guess. So how do you get a completely literal, unthinking machine to execute a delicious outcome?
Well, consider a typical vague recipe. Something like, take some milk, put crush, blend. If you give that to a machine, it completely fails. Why? Because it lacks context. It has no idea where to get the milk or where to put it. What it actually requires is an explicit, precise master plan. You have to tell it, pour exactly 1 glass of milk into the mixer jar. Add the crush, close the lid, switch it on. It needs explicit amounts, specific containers, and precise start and stop triggers.
And just like that perfect milkshake recipe, the instructions we feed a computer must follow strict, unforgiving rules. First, they must be sequential, flowing in a perfectly logical order. Second, they have to be finite. I mean, you definitely don't want a blender running for all eternity, right? And third, they must be completely accurate. Without sequence, a limit, and accuracy, the machine simply cannot compute. It's just a metal box.
Section 1. From commands to software.
Translating our recipe analogy directly into the digital world reveals a really clear hierarchy. At the absolute base, an individual instruction, like pour the milk, is what we call a command. Group a bunch of those commands together to accomplish a specific task, and boom, you have a program. But what happens when a job is too complex for just one program? Well, you integrate several of them to work in tandem, and that whole integrated set, that becomes software.
Section 2. Meet the C language.
Now, C didn't just appear out of nowhere. It actually evolved over time. Back in the 1960s, Martin Richards developed BCPL, which Ken Thompson then adapted into what he called Language B. Finally, in the early 70s, over at Bell Labs, the legendary Dennis Ritchie created Language C for the Unix operating system. And here's the real game changer. While its predecessors were completely typeless, C introduced a variety of data types, like characters and integers, which made it a massively versatile tool.
C holds a really unique position as a middle-level language. It acts as the ultimate bridge. On one side, it utilizes the structured, human-readable logic that you find in high-level languages, but on the exact same token, it allows for direct manipulation of a computer's most basic elements. We're talking raw bits, bytes, and memory addresses, which is usually stuff reserved for low-level assembly languages. That duality is exactly why C absolutely dominates system-level programming.
Section 3. Anatomy of a C program.
The syntax of C is strict for sure, but it's surprisingly lean. It's built on just 32 native, heavily protected keywords. For starters, it is entirely case-sensitive, and keywords must be lowercased. For example, write do while in lowercase, and the computer executes it beautifully. Write it in uppercase, the compiler throws an error. No way around it. Furthermore, these 32 keywords are strictly reserved. You literally cannot co-opt them for your own functions or variable names. They belong to C.
When you read a C program from top to bottom, a very distinct anatomy emerges. Control is always passed first to the main function. That is your absolute starting point. From there, you'll see curly braces acting as delimiters to contain specific blocks of code. Inside those blocks, semicolons act as terminators. They end statements just like a period ends a sentence in English. And sprinkled throughout, you'll find comments wrapped in /asterisks. Those are notes meant purely for human eyes. The machine will entirely ignore them.
Section 4. Code to execution.
So how did these raw text ingredients actually blend into a working application? Well, it takes an amazing journey from human thought down to an executable reality. The original source file gets passed through a compiler to generate an object file. That object file is then run through a linker, paired up with standard library files to finally produce the executable file.
Think of these steps as your kitchen appliances for code. First up, the preprocessor preps your ingredients by expanding directives. Those are the statements that start with a hashtag. Next is the heavy lifter, the compiler. It takes your human-readable text and translates it directly into machine language, creating that object code. Finally, the linker acts as the blender. It mixes your object code with pre-made support routines from standard C libraries, fusing the whole shebang into final executable software.
And that brings us full circle. Computers possess lightning-fast computing power, but absolutely zero independent intelligence. They are just waiting on you. They just sit there, ready to follow sequential, finite, and accurate instructions. You now know the recipe for programming and the fundamental architecture of the C language. You've got the grammar, you've got the tools. The only question left is, with all that raw power waiting at your fingertips, what are you going to build next?